7 months. That is how long it takes to reach Mars on a chemical rocket. 210 days sealed inside a metal tube the size of a small house. No resupply, no rescue, no turning back. 210 days of cosmic radiation bombarding every cell in your body at doses that significantly raise your lifetime cancer risk. 210 days of muscle wasting as your body quietly forgets how gravity works. 210 days of psychological pressure that has broken test subjects in controlled simulations right here on Earth. And then you arrive, exhausted, weakened, irradiated. You step out onto the surface of Mars. And in roughly 18 months, when the planetary alignment finally allows a return window, you climb back into the same metal tube and spend another 7 months going home. That is the mission as currently planned. That is what NASA is asking astronauts to endure. And that is what makes the technology we are about to discuss the most important engineering project in the history of human space exploration. Because NASA and Defense Advanced Research Projects Agency have been developing a rocket engine that does not burn chemical fuel. It burns atoms, and it can reach Mars in 45 days. This is the nuclear rocket. This is why it was canceled. And this is why the people who built it believe it will come back. Section 1 scene, why chemical rockets hit a wall. To understand why a nuclear rocket changes everything, you first have to understand why chemical rockets have reached their absolute physical limit. Every rocket ever built by human civilization, from the V2 to the Saturn V to the Falcon 9 to the Space Launch System, works on the same fundamental principle. You take a fuel and an oxidizer. You burn them together in a combustion chamber. The burning creates hot expanding gas. You direct that gas through a precisely shaped nozzle. The gas exits at extremely high velocity. Newton's third law does the rest. For every action, an equal and opposite reaction. Gas shoots backward, rocket goes forward. The performance of any rocket engine is measured by something called specific impulse. It measures how efficiently a rocket uses its propellant. The higher the specific impulse, the more thrust you get from the same amount of fuel. The best chemical rocket engines ever built. The Space Shuttle main engine, the Merlin engine, the RS-25 achieve a specific impulse of roughly 450 seconds. 450 seconds is the chemical wall. It is dictated by the temperature at which hydrogen and oxygen combust. You can optimize the combustion chamber. You can perfect the nozzle geometry. You can refine the fuel mixture ratio to the last decimal point. But the fundamental energy released by burning hydrogen and oxygen has a ceiling. And we have been operating right at that ceiling for 50 years. This ceiling dictates everything about a Mars mission. Because the farther you want to go, the more fuel you need. And the more fuel you carry, the heavier your spacecraft gets. And the heavier your spacecraft, the more fuel you need to accelerate it. It becomes a tyrannical feedback loop that engineers call the rocket equation. Konstantin Tsiolkovsky derived it in 1903. It has not changed since. It is one of the most punishing mathematical relationships in all of engineering. For a chemical rocket, a Mars mission requires carrying an extraordinary mass of propellant. Most of what you launch is fuel. The actual spacecraft, the crew quarters, the life support, the science equipment, the landing hardware, represents a small fraction of the total mass sitting on the launch pad. The rest is propellant that gets burned and thrown backward into space. The transit time to Mars is a direct consequence of this fuel limitation. You cannot simply burn the engines continuously to go faster. You light the engines for a relatively brief burn to set your trajectory, then coast for months on the ballistic arc that trajectory creates. 7 months of coasting through deep space, exposed to everything the void has to throw at you. There is only one way to break the Tsiolkovsky equation. You have to change the energy source. You have to go nuclear. Section 20A, the physics that changes everything. A nuclear thermal rocket does not burn fuel in the conventional sense. There is no combustion, no oxidizer, no flame. Instead, at the heart of the engine sits a nuclear fission reactor. Uranium fuel rods arranged in a precise geometric configuration begin a controlled chain reaction. Neutrons split uranium atoms. Each split releases energy. The released neutrons split more atoms. The chain reaction sustains itself, releasing an enormous and continuous flux of thermal energy. In a chemical rocket, that heat would come from burning hydrogen. In a nuclear thermal rocket, the reactor generates heat at temperatures far beyond anything chemical combustion can achieve. The reactor core reaches approximately 2,700 Kelvin. For reference, the surface of the Sun sits at approximately 5,700 Kelvin. The reactor is operating at nearly half the temperature of the surface of the Sun. Through that superheated reactor core, engineers pump liquid hydrogen at cryogenic temperatures, minus 253 degrees Celsius. The hydrogen enters the reactor as a cryogenic liquid at 20 Kelvin. It exits as superheated plasma gas at 2,700 Kelvin. The temperature ratio between entry and exit is roughly 135 to 1. That superheated hydrogen gas expands violently and is directed through a precisely engineered nozzle. The exit velocity of the gas is dramatically higher than anything achievable through chemical combustion, because velocity is a function of temperature, and the nuclear reactor reaches temperatures that hydrogen-oxygen combustion simply cannot match. The result is a specific impulse of approximately 900 seconds, twice the best chemical rocket engine ever built. Double the specific impulse does not mean double the speed. The mathematics are more complex and more profound than that. Double the specific impulse means that for the same amount of propellant, you can accelerate a spacecraft to significantly higher velocities. Or you can carry dramatically less propellant to achieve the same velocity as a chemical rocket. Less propellant means lighter spacecraft. Lighter spacecraft means faster acceleration. Faster acceleration means shorter transit times. Shorter transit times means less radiation exposure. Less radiation exposure means living astronauts arrive at Mars. The 45-day figure for Mars transit is associated with advanced nuclear propulsion architectures where the engine burns continuously or near continuously during significant portions of the transit. Even near-term nuclear thermal rockets using the principles we have just described can cut the Mars journey from 7 months to 3 to 4 months. Every month removed from that transit is a direct, measurable reduction in the radiation dose absorbed by the crew. This is not theoretical. The physics are settled. The engineering has been proven. We know it works because America built it and tested it over 50 years ago, and then buried it in the desert. Section 3DZ, Nuclear Engine for Rocket Vehicle Application. The engine America built and abandoned. In 1955, the United States government launched a classified program called Project Rover. Its objective was to develop a nuclear thermal rocket engine capable of propelling spacecraft to Mars and beyond. The program ran for 17 years. It was funded at levels that would represent billions of dollars in today's terms. It employed some of the finest rocket engineers and nuclear physicists in the country. It worked. The Nuclear Engine for Rocket Vehicle Application Program, Nuclear Engine for Rocket Vehicle Application, produced engines that were tested 28 times in the Nevada desert. Not simulated, not modeled, actually fired. Hot nuclear reactor, liquid hydrogen pumped through the core, superheated gas out the nozzle, thrust measured on test stands in the real world. The Nuclear Engine for Rocket Vehicle Application's prime engine ran for over an hour at full power in 1969. The same year Neil Armstrong walked on the moon, America had a functioning nuclear rocket engine sitting in the Nevada desert. The specific impulse achieved in those tests was 840 seconds. Double the Space Shuttle main engine. NASA's plan in 1969 was to use nuclear engine for rocket vehicle application engines to send humans to Mars by 1978. The trajectory was clear, the technology was proven, the hardware existed. And then Richard Nixon canceled the program in 1972. The official reason was budget pressure. The Apollo program was winding down. Congressional appetite for large NASA expenditures had cooled dramatically. The Vietnam War was consuming federal resources. Nuclear engine for rocket vehicle application was canceled along with the planned Mars mission as part of a broad reduction in NASA's ambitions. But the engineering did not disappear. The test data was archived. The fuel fabrication knowledge was stored. The reactor design principles were documented. 28 successful engine tests do not vanish, they wait. For 50 years, the nuclear engine for rocket vehicle application knowledge sat in archives. The people who built it aged and died. The test infrastructure in Nevada was decommissioned, and chemical rockets continued to define the ceiling of human access to deep space, pushing against the same Tsiolkovsky wall that nuclear engine for rocket vehicle application had already broken half a century earlier. Section 40A, the return of the nuclear rocket in January 2023, NASA Administrator Bill Nelson stood at a podium and made an announcement that should have dominated every science headline on the planet. NASA and the Defense Advanced Research Projects Agency were formally partnering to build and test a nuclear thermal rocket engine in space. The program was called Defense Advanced Research Projects Agency, Demonstration Rocket for Agile Cislunar Operations. The total program budget was $499 million, split between the two agencies. NASA would lead the technical development of the nuclear engine. Defense Agency would lead the spacecraft integration and launch operations. Lockheed Martin was selected as the prime contractor responsible for the spacecraft design and integration. Babox Technologies, based in Lynchburg, Virginia, was contracted to design and build the actual nuclear fission reactor. The target was a 2027 demonstration flight in Earth orbit. Not a Mars mission, not a crewed flight. A proof of concept orbital test designed to verify that a nuclear thermal engine could operate safely and effectively in the space environment. But the engineering at the heart of Defense Agency was directly derived from the nuclear engine for rocket vehicle application heritage. 50 years of archived test data, 50 years of fuel research, 50 years of reactor design knowledge, all of it pulled back out of storage and applied to a modern design. The fuel was different. Nuclear engine for rocket vehicle application had used highly enriched uranium, weapons-grade material that created enormous regulatory and security complications. Defense Agency used high-assay, low-enriched uranium HALEU, a fuel enriched to between 5 and 20% uranium-235. Still highly technical to manufacture, still requiring careful handling, but not weapons-grade material. An important distinction for regulatory approval of an orbital nuclear test. The reactor design at the core of Defense Agency was a graphite, composite structure, uranium fuel elements distributed through a graphite moderator, liquid hydrogen flowing through channels in the fuel elements, and absorbing the reactor heat as it passed through. The Defense Advanced Research Projects Agency Program Manager Juter Tabitha-Sun described the engine's performance in terms that should have silenced every critic. Nuclear thermal propulsion offers a thrust to weight ratio 10,000 times greater than electric propulsion systems, 2 to 5 times the specific impulse of chemical engines. In practical terms, for a Mars mission, a nuclear thermal spacecraft could carry more crew, more supplies, more science equipment, and still arrive faster than any chemical mission ever could. The implications were clear. If the 2027 demonstration succeeded, the path to a crewed Mars mission with transit times measured in weeks rather than months was technically achievable within a generation. Section 5V. The cancellation on May 30, 2025, the finalized federal budget for fiscal year 2026 was submitted by the Trump administration. Defense Agency was canceled, not delayed, not restructured, not reduced, canceled. With zero funding allocated to nuclear thermal propulsion or nuclear electric propulsion in the entire NASA budget going forward. The Space Technology Mission Directorate, the NASA division responsible for Defense Agency, and dozens of other advanced technology programs, faced a proposed $531 million cut. The budget documentation cited reductions in unspecified advanced space propulsion projects. The political framing was that the programs were expensive and that decreasing commercial launch costs and new analysis had made them less necessary. Defense Agency completed its program termination procedures and transferred the accumulated technical knowledge back to NASA. The contracts with Lockheed Martin and WX Technologies, which had been progressing toward the 2027 demonstration flight, were wound down. The engineers who had spent years pulling the nuclear engine for rocket vehicle application knowledge out of archives, adapting 50-year-old reactor designs to modern materials and manufacturing techniques, solving the regulatory challenges of flying a nuclear reactor in Earth orbit. Those engineers now watched the program die in a budget document. For the second time in American history, a functioning nuclear rocket program was canceled not because the physics failed, not because the engineering failed, but because the political will failed. And here is the consequence that no budget document will ever honestly state. Every month that a crewed Mars mission spends in transit is a measurable biological cost. A 7-month chemical rocket transit delivers a radiation dose that permanently and measurably increases a crew member's cancer risk. A 3-month nuclear transit cuts that dose nearly in half. A 45-day transit, achievable with more advanced nuclear propulsion architectures that Defense Agency was designed to evolve toward, changes the biological math of a Mars mission entirely. When you cancel nuclear propulsion, you are not canceling a technology demonstration. You are condemning future astronauts to months of additional radiation exposure that a machine we already know how to build could have eliminated. Section 60 Psi, how the engine actually works. The engineering in detail before the program was canceled. WX Technologies and Lockheed Martin had published enough technical detail to understand exactly what Defense Agency's nuclear engine was designed to do and how it did it. The reactor core is the size of a large engine block. Inside it, hundreds of fuel elements, hexagonal rods of uranium fuel embedded in a graphite composite structure, are arranged in a precise geometric array. The geometry is not arbitrary. It is calculated to maintain a controlled, sustained chain reaction at the exact thermal output required for the engine's operating point. Flowing through channels bored through each fuel element is liquid hydrogen. The hydrogen enters the reactor from a cryogenic tank at 20 Kelvin, roughly the temperature of deep space itself. As it flows through the channels in the uranium fuel elements, the reactor heat transfers directly into the hydrogen. By the time the hydrogen exits the reactor, it is no longer a liquid. It is a superheated plasma gas at temperatures exceeding 2,700 Kelvin. This superheated hydrogen gas is then directed through a converging diverging nozzle, the same basic geometry as a chemical rocket nozzle, but scaled to handle the higher temperatures and flow velocities that nuclear heating produces. The control system that manages this process is intricate. Rotating control drums embedded in the reactor's reflector structure, cylindrical drums with neutron-absorbing material on one face, control the chain reaction by rotating toward or away from the reactor core. Rotate toward the core and the drums absorb neutrons, slowing the reaction and reducing power. Rotate away and more neutrons remain in the core, accelerating the reaction and increasing power. The entire system, reactor, controls, hydrogen pump, nozzle, is designed to operate in the vacuum of space, away from Earth's magnetic field protection, at radiation levels that would destroy conventional electronics. Every component must function in an environment where there is no atmosphere to convect away waste heat, no maintenance crew to replace worn parts, and no recovery option if something fails at maximum power 200 million kilometers from Earth. The specific design challenge that took the most engineering effort was not the reactor itself. It was the turbopump. The liquid hydrogen propellant is stored at cryogenic temperatures in insulated tanks to flow it through the reactor at the required rate. A turbopump must pressurize it from tank pressure to reactor inlet pressure while simultaneously handling a fluid that is super cold, low in density, and violently reactive with any trace moisture or oxygen. The turbopump must operate across enormous temperature ranges, from cryogenic liquid on the inlet side to hot gas on the turbine side, without mechanical failure. Box's solution drew heavily on turbopump heritage from chemical rocket programs while adapting the seal designs, bearing materials, and turbine blade geometries for the specific conditions of a hydrogen-cooled nuclear engine. Every system on Defense Agency was designed to be tested in space before being committed to a crewed mission. The 2027 demonstration flight was intended to run the reactor at multiple power levels, measure the actual specific impulse achieved against the predicted value, verify the control drum response times, validate the thermal management systems, and confirm that the nuclear exhaust plume dispersed safely in the orbital environment without creating regulatory concerns for future operations. None of that testing will happen in 2027. Section 7A, What America Loses. The 45-day Mars transit figure is real, but requires important context. Term nuclear thermal engines like Defense Agency's design, achieving specific impulse around 900 seconds, would cut the Mars journey from 7 months to approximately 3 to 4 months. Still transformative. Still a profound improvement in crew safety and mission capability. The 45-day figure requires a more advanced nuclear propulsion architecture. Nuclear pulse propulsion, continuous burn nuclear thermal systems, or nuclear electric propulsion running high power ion drives over the entire transit. These are the next generations of the technology architectures that Defense Agency was the foundational step toward demonstrating. You cannot build the advanced systems without first proving the basic nuclear engine works in space. Defense Agency was that proof of concept, the canceled stepping stone. Consider what the competition is doing. China's nuclear propulsion research program has been classified but active. Russian theoretical work on nuclear thermal propulsion predates even the American nuclear engine for rocket vehicle application program. Both nations understand what these documents make clear: whoever solves crewed deep space transit first owns the strategic high ground of the solar system. America canceled its nuclear rocket program in 1972. It spent 50 years rebuilding the capability. It canceled it again in 2025. The nuclear engine for rocket vehicle application test data is still in the archives. The Budox reactor design work is still on file. The Lockheed Martin spacecraft integration knowledge still exists in the engineers who worked on it. The physics have not changed. The specific impulse of a nuclear thermal engine will always be double that of the best chemical engine as long as thermodynamics governs the universe. The question has never been whether nuclear propulsion works. It works. 28 engine tests in Nevada a half-century ago proved it works. The Defense Agency design work confirmed the engineering path forward. The question has always been whether the human civilization building these machines has the patience and the political will to finish what its engineers start. Somewhere in a federal archive, the nuclear engine for rocket vehicle application test data still sits next to the Defense Agency design files, waiting again for the third attempt, closing 45 days. 1 month and 2 weeks, the time it takes to drive across the United States 14 times, the duration of a university semester, the length of a moderately ambitious vacation, 45 days to reach another planet. The physics that make it possible have been understood for 70 years. The engineering that would build it was proven in the Nevada desert 50 years ago. The modern program that was rebuilding it was canceled 11 months ago. There are astronauts alive today who will be asked to make a 7-month journey to Mars on a chemical rocket if nothing changes. 7 months of radiation. 7 months of muscle degeneration. 7 months of psychological isolation in a vehicle moving through the most hostile environment in the known universe. They will make that journey because they are astronauts, and that is what astronauts do. But they will know that somewhere in a government archive, there is a design for an engine that could have gotten them there in 45 days. An engine that was funded, contracted, actively being built, and then canceled in a budget document that nobody outside of aerospace engineering circles will remember in 5 years. The nuclear rocket will come back. It always comes back. The physics make it inevitable. The survival mathematics of a crewed Mars mission make it necessary. The strategic competition with other spacefaring nations will eventually make it urgent. The only question is how many years of chemical rocket transits we accept before the political will catches up with the engineering knowledge we have already accumulated. NASA built a nuclear rocket. It worked 50 years ago. It was being rebuilt. And then we canceled it. Again. If you want to follow the engineering that will define the next century of human civilization, subscribe. Every week we go to the frontier of what human beings are building. And sometimes, what they are choosing not to build.